I'm recording the meeting now. If you're watching this back, my apologies, we've missed the first couple of slides, but you'll figure it out. Okay, general diffusing. Diffused light is a soft light with neither the intensity nor the glare of direct light. It is scattered and comes from all directions. The general diffusing type of luminaire is used as lighting for homes, shops, and some offices. It relies on the walls and ceilings being clean and light in color to reflect and produce an even spread of light. Midway between the direct and general diffusing luminaires is the semi-direct luminaire. Many modern fluorescent luminaires and incandescent lampshades are semi-direct, making them useful in offices, shops, and homes. Semi and direct luminaires have many of the advantages of indirect luminaires, but are more efficient. They produce the soft shadow, non-glare type of lighting commonly used in boardrooms and reception units. Yeah, so all of that is stuff that we've talked about. There's one little point there about efficiency. As you can perhaps imagine, that the more indirect our lighting is, the greater the chance that we lose some of that light. If I have a direct light, then I have all of my light shining on the thing that I want it to shine on. So I could potentially use a lower wattage light fitting because I only need the light in that area. And once I have enough light in that area, then it's pointless for me to add more. With a really heavily indirect setup, whilst we're getting that uniformity, what we're doing is the way we get that uniformity is that we scatter the light everywhere, which means we probably need an overall higher light level because we're going to, if I need more light where I'm working, I'm going to need to light the whole space more because we're going for a really uniform effect. So even to raise the lux a little bit in one space, we've now got to raise the light level across the entire room. And hence, again, if we think of our classroom or any other office space, there's a lot of light fittings in those type of places. We've got a very high general lighting level. So that's perhaps one of the disadvantages of indirect lighting. Just remember, team, if you have questions as we go, I'll just smash through this. But if you have questions as we go, type it in the chat. Jump on your microphone if you want to. Yeah, whatever. I'll stop at various points to ask for questions, but feel free to jump in if you need to. Okay, so here we've got a table that's giving us some of the advantages and disadvantages of different types of lamps. I won't go into this in detail. You can read that for yourself. Note here that actually, can you guys see my mouse on the screen? Cool. So if we look here, surface mounted incandescent, reset incandescent. So we're just talking about standard general light fittings. Same with a low voltage halogen. Neon, low pressure sodium, high pressure sodium, mercury vapor, and metal halide are all gas discharge type lamps. We'll do a topic on gas discharge today or tomorrow. So we'll learn more about those. And then the last two are obviously self-explanatory, fluorescent and LED. So we haven't gone into the gas discharge stuff much yet. So some of those advantages and disadvantages might not make perfect sense. If we look at the incandescent type lights, so the top three there, they're all those incandescent types, which means we have a burning filament. They tend to be inexpensive in that it doesn't cost me much to buy the light bulb itself. It doesn't cost much for the fittings usually. The downside is from a cost perspective that they're going to cost a lot of money to run them. I mean, not huge amounts, right? A 100-watt light bulb is still only 100 watts, but multiply that by 30 across a house compared to something that, like an LED that as we looked at last week, might be up to 10 times more efficient, and there is a significant cost difference there in terms of running them. You see here, and the recessed incandescent, it also says that there's fire risk there. remember that with an incandescent, probably the primary disadvantage, and this is why they're reasonably inefficient compared to other types of lighting, is that the incandescent, like I said, it's just a burning filament, so it's creating a lot of heat along with the light. So that heat gives us that potential for a fire risk if not installed correctly. We won't talk too much about the next ones, the gas discharge lights, because as I said, we've got a whole topic on that. The gas discharge ones, though, all tend to be pretty efficient, so we're getting a reasonably high light output for the input value. The biggest disadvantages you'll find with your most gas discharge type lighting is the color rendering. My apologies if I cough my lungs out. Sorry about that. Yeah, with our gas discharge type lighting, is our color rendering. Now, we haven't talked about color rendering too much. This is related to, but slightly different to the actual physical color of the light, right? So the color of the light is one thing, and then color rendering is a little bit different. So color rendering means how colors look under that light. If you've ever stood under one of those really yellow street lights, which on here is the low pressure sodium, you'll know what I mean, because everything looks washed out and really strange. It gives you that yellow hue across everything because the light it's putting out is yellow, but it actually changes the way that colors look to the eye. So you'll find that it can be quite tough to tell the difference between like green and red, for example, under a low pressure sodium light. They just kind of start to blend and look the same, which I guess maybe that's probably what colorblind people are seeing. So in any sort of situation where we have people working or occupying an area for long periods of time, doing anything detailed, color rendering is really important. You would think, who cares, like what colors look like, what difference does it make? But again, if you spend any period of time under lights with poor color rendering, you'll find that it's a very uncomfortable experience. Not necessarily for your eyes, but for your brain. Everything just looks strange and washed out, and it just gives you an odd sort of feeling. So that's generally our biggest limitation around gas discharge lighting, is that color rendering. Hence why, as you'll see on here, that we're generally talking about industrial street lighting or various types of exterior lighting, like maybe car parks and stadiums and that sort of stuff. That's where we tend to use gas discharge lighting, or most of these types of gas discharge lighting, because the color rendering is poor. So we don't want to use those in an area where people are going to be occupying. It's just in areas where we just want lots of light, and it doesn't matter what the quality of that light is. I guess it's prudent to note here that quality of light is really, really important. We don't think about it much. But I guess that's why we go through these topics, right? You might be sitting there going, a lot of this stuff seems really strange. Who honestly gives a shit about colors and brightness and diffusion and all of that stuff? But if it doesn't mean much to you, that's probably because most of the spaces that you occupy, whoever has designed the lighting for those areas has done a pretty good job. Because if they're doing a good job, we don't notice it. Things just look normal. When you're in an area where this has not been done well, where the lighting design has not been done well, then you notice, right? Things look strange, or there's not enough light, there's weird shadows, that kind of stuff. So whilst it seems like something that's just really obvious, that's only because people do it, and we get to wander around in the world where the lighting plans have been done really well, and we don't have to think too much about them. With our gas discharge, again, our best advantage here is usually efficiency. efficacy. These most gas discharge lights tend to output a lot of light with not much energy input, so that's a good thing. Although, again, these days, LEDs will rival all of the gas discharge lamps for efficacy. There might be one or two of the gas discharge ones that might give you a slightly better efficiency than LEDs, but the quality of light out of an LED is likely to be so much better. So if you're talking about a few cents an hour difference in efficiency from, say, a low pressure sodium to an LED, as in the low pressure sodium is still maybe slightly more efficient, the quality of light out of an LED is so much better that you might as well put it in there. Plus the overall lifetime of an LED will be far in excess of anything else. So even if it's a cost related thing, you'll probably find that the LEDs will beat most types of gas discharge lighting for cost in the long run. Another inefficiency, or rather another disadvantage of gas discharge lighting, is they tend to be fairly expensive to install, or fairly expensive to purchase. The lamps themselves can be pretty expensive. From memory, and this is probably going back 10 years to the last time that I've done any genuine maintenance work on gas discharge lamp fittings. Some of them, like your metal halides and mercury vapors, you can get your 400 and 500 watt bulbs, which are pretty big. They might cost like $200 each. They'll probably last 10 years, but just think about that. If you've got a site with 10 or 20 of them in there, and it's $200 to replace a bulb, it's fairly expensive. And then the initial startup cost is pretty expensive as well. They tend to have some fairly complicated control gear, which again we'll get into when we discuss the discharge lighting specifically. They have fairly expensive control gear because we're talking about quite high voltages involved, striking arcs and stuff like that. So it might be $500 to $1,000 just to buy the fittings. Okay, so moving down from gas discharge then to the fluorescent. Fluorescent is a type of gas discharge lighting as well. It's a slightly different setup, but I guess it does count as gas discharge. We're all familiar with fluorescent lighting, so we would have seen these in a million places. They're really energy efficient, they're fairly cheap to install, and they have a reasonably long life. As it says in the thing here, we can get good a range of different colors for different situations. So fluorescents over the years have been extensively used, particularly in commercial spaces, right, office spaces and that kind of thing. Now, saying that, in the modern day, in probably the last 5 years, we've seen that all of the advantages that fluorescents have given us, LEDs tend to be slightly better on every single one of those. So your LED has an even better energy efficiency. It has an even longer lifetime. We get all of the same color temperatures. The cost is probably on par. The LEDs might be slightly more expensive, but certainly when you factor in the lifetime costs with energy efficiency and the length of life, LEDs are far cheaper than fluorescents over the long run. And then the downsides of the fluorescent tubes, as it says, is stroboscopic effect, which is a fast flicker. It's faster than our eyes can pick up, but it does affect us. And the maintenance costs of changing tubes and ballasts and starters and stuff like that. You don't have either of those downsides with LED lighting. So whilst there are some really great advantages of fluorescence, again, I might have mentioned this last week, but we will see in our lifetimes that LEDs will certainly take the place of both fluorescents and incandescent lamps. everywhere where those are currently used. We just will not see them anymore. By the end of our lifetimes, and possibly even by the end of my working career, which is probably only 25 years away, the fluorescence and incandescent lamps will be essentially a distant memory. We happy with that? Any questions so far? Thank you, Narendra. That's a great question, Ray. Are you talking about the flickering as it's starting, or just general flicker while it's in operation? Okay, let me think about that for a second. You will tend to see flickering on startup a lot more as the tube gets older, and that can be to do with ballast starting to fail and starters starting to fail. Why do they flicker? Okay, so what I say is, in the end of each fluorescent tube, you have a little heater. What do we call that normally? Maybe just heater. So it's just a little coil, and that heats the whole tube. That helps to keep the gas ionized. As the heater starts to burn out, you can get the gas deionizing, and that'll start to cause that flicker. Sometimes you'll see that as like a shadow that runs up and down the tube, or a bright spot that runs up and down the tube. Has anybody ever seen that before? Okay. No. Okay. Fair enough. Yeah, so it's probably due to the heater starting to burn out, or running less efficiently. I mean, that doesn't feel like a very good answer, to be honest with you, and I apologize that I don't have a great answer off the top of my head. Generally though, once a fluorescent tube ignites, it will remain ignited, right? We need that high voltage pulse to ionize the gas. But then once it's ionized, it'll tend to stay operating. So you will definitely see a lot more flicker on startup as a fluorescence gets to the end of its lifetime. Perhaps flickering in general is a little bit less common, but yeah, as I said, or as you say there, Ray, it does happen, and it's probably due to do with those heaters. Yeah, maybe not the best answer in the world, but that's all I got right now. When we get into that topic, we do talk about fluorescence a bit more. There'll be more details in there. And while I think about it, actually, while we're doing online lessons, I know that I'm not gonna stop us to watch videos, but I can tell you that throughout this lighting stuff here, the videos that we've got on Canvas are really, really good. They all tend to be pretty short, so you can just consume them in bite-sized chunks, sort of 2 to 5 minutes. But the information that's contained in those videos is really, really, really useful, and you'll find that it helps to clarify a lot of things that I'm saying, because the people who are making those videos know shitloads more about lighting than I do. And in fact, I think when we get to the gas discharge one, there's a bunch of videos that are all made by the same guy. It's like this really weird dude who's like you watch the videos and he's genuinely getting, you can tell that he gets his jollies from lights. It's a bit strange. He's like some hermit looking dude that lives in Las Vegas or something. But But I actually really enjoy those videos because he's super into it, and he, this is just this guy talking off the top of his head and saying, this is a metal halide lamp, and it works like this, and it does this, and these were first invented by James Anderson in 1946, and he was actually trying to do this, and he accidentally came across this, and then his mate Dave did this, and like he goes right into it, knows all of the stuff. It's really, really interesting. So please, I know that your online classes, there's a real temptation here to sit here and listen to me and then do your test and move on and forget about it, because you can go and watch telly instead, or have a sandwich, or whatever else you'll do with your life when you don't have to be in class. But please go and watch those videos. They're really good. It won't take much time, and you probably get as much information and value out of those videos as you will getting out of listening to my entire spiel on these slideshows. Anyway, Ray, are you happy with my answer, or happy enough for now? Yeah, okay, cheers, mate. We've looked at this slide before. It's the same table as we saw in the earlier one. Again, this is showing us our average lumen outputs compared to wattage, and you can see the different efficiencies that we're getting here. It doesn't have the low pressure sodium. From memory, I think the low pressure sodium is the only light that really rivals LEDs for genuinely output compared to wattage. If you look here, it looks, off the top of my head here, it looks like the high pressure sodium is the most efficient. So we get about 35,000 lumens from a 400 watt high pressure sodium lamp. If you remember last week, we said that a LED, we might get something like 9 or 10 lumens per watt. 9 or 10 lumens per watt. Yeah, that sounds about right. So with an LED, then we're talking about, for a 400 watt lamp, if we look at this bottom row here, for a 400 watt lamp, 9 or 10 lumens per watt would give us a light output of 36 to 40,000 lumens for a 400 watt LED lamp. So you can see there, just using that rough guideline of 9 or 10 lumens per watt for LED, you'll see that in efficiency, it's going to, again, is generally much more efficient than even these gas discharge lights, which the primary advantage of those gas discharge lights is the efficiency, the amount of light we can get out for every watt of power that we put in. So if an LED is far more efficient than those, and then we don't have the disadvantages of the complicated control circuits, expensive fittings because of that complexity, and that relatively poor color rendering that we're likely to see with most of these gas discharge lights, then you can see why an LED becomes a better option. Now, as I said, that we haven't got the low pressure sodium there. That the low pressure sodium is that, again, that yellow street light. The yellow street lights, you still see them around. The low pressure sodium has the best efficiency of any type of lighting, and that might, I think off the top of my head, that might be the only one that still will be a little bit more efficient than LED. But the downside of the low pressure sodium is it's got such poor color rendering. It's really that really yellow color that makes everything look ugly. And here again are our lumen outputs of fluorescent tubes, which I won't go through again. We've seen this before. Well, the only thing I'll say on this is these color codes here can be useful if you can memorize them. Okay, that's helpful when you walk into the wholesaler and you say, I want a 55, a 65 watt 55, and that'll tell the wholesaler what color tube you're after. Luminous efficacy we've seen before. This is simply calculating the output or the efficiency of our lights in terms of lumens per watt. I talked about this all of the last few slides, our lumens per watt efficiency is one of our most important factors when we're designing lighting, right? For obvious reasons, especially if we're lighting a large area or we want particularly bright lighting. That luminous efficiency, luminous efficacy, it tells us how much it's going to cost over time, right? So, you know, the stark example there is the difference between an incandescent and an LED. If we can get nearly 10 times the lumen output from an LED that we get from an incandescent for the same power input, the same number of watts, those are going to far outstrip the incandescents over time in terms of the cost of running that thing, and that's, I guess, the primary reason why again, as I said, that LEDs will become the only source of lighting at some point in our lifetime, unless of course we come up with something better, which, you know, the rate of technological change in the world at the moment suggests that there's no reason why we wouldn't. So the calculation of our luminous efficiency is really simple. It's just that a light output is a flux and divided by the power input. It gives us a figure in lumens per watt. So if I have 100 lumen bulb and it consumes 10 watts of power, it's 100 divided by 10, which means 10 lumens per watt, which I think that's pretty simple. Does that make sense to everybody? Is anybody confused by what I'm saying there? I'll take your silence to mean that we are all fairly happy with that. Okay, thank you, Max. Again, we've seen this table before. This is our rough benchmark of light levels required in different areas. And all I'll say about this is, as I said last week, you'll find that the more detailed work requirements, the higher the light levels. So if we look here, fine work, electronics and office, or very fine work, we want very high light levels. So 1,000 to 1,500 lux. Whereas if we're talking about corridors, lifts, stairs, escalators, as I said last week, you know, areas that we're just passing through, we only need enough light there to stop us falling over our own feet. We'll tend to see much lower light levels. What else was I about to say? Give me a second, please. All right, so these numbers here, remember, those are measurement of lux on a given spot, right? So that's where we would use the light meter, and it tells us how much illumination is actually reaching that given point. So this is not the same as the illuminance, which is our total light level in lumens per square meter. This is the specific amount of light that's reaching a given point. So that's where you use that light meter. Actually, something that has just occurred to me, all of these things are only relevant in the sense, when I say all of these things, I mean that the lighting levels in given areas are only really relevant in the sense that lighting costs money to produce, right? So if we think back to our incandescent lamps, which are our least efficient lamps in terms of the amount of light they give out per watt, numbers like this are important, right? Because the more light I produce, the more money it costs. If you think of a big building, if you think of the MIT Tech Park, that's a big building with a shitload of lights in it. So if we were lighting that building with incandescent lamps, then the actual cost of lighting it on an hour-to-hour, day-to-day basis is an important factor. Because if I can reduce the light level, so if we look here, the difference between very fine work being 1,500 lux compared to, corridors and stairs maybe being 150 lux, that's 10 times. So I can reduce my cost to light certain areas by a factor of 10 because I don't need that much light there. I think that would make sense to everybody. That's a fairly obvious statement. If we take that one step further, we realize that, you know, in the age of the LED, and LEDs are likely to get more efficient. And as I just said, it's potentially possible that we would see other types of lighting developed that may be even more efficient. And actually, some of these numbers become less valuable, right? Because if it costs me nearly nothing to actually produce that light, you know, if we've gone from incandescents to LEDs, where the cost, the power cost to run those lights is 10 times less, then actually it probably doesn't matter that much. I don't have to reduce the lighting in on the stairwells to 150 lux because it doesn't cost me that much to make it higher. So that might actually be something that, again, that we see in the next perhaps 10 to 20 years as people become more and more used to much more efficient lamps, that maybe lamps will become even more efficient than they already are, that these sort of calculations in terms of your baseline lighting levels might become somewhat redundant, because we might just decide to uniformly light every area, because why not? It doesn't cost much to do it. And in fact, if I think about it, I would have to have a look, and maybe you should as well. But if I think about Tech Park, MIT, I can't think, like, off the top of my head anyway, I don't think that the lighting levels are particularly different in one area to another. If we think about those little foyers and the stairwells between classrooms upstairs, I don't think they have lower lighting levels in there. So maybe that's already starting to take effect. That you know, try hard, say hard word, proliferation of much more efficient types of lighting has meant that these benchmarks are becoming a little bit less useful. Nevertheless, these are what the international standards are. And I think this is out of an international standard. You know, some nerds somewhere, probably in Belgium, have got together and come up with a little list of how much light you should have in different areas. Okay, inverse square law. Right, so we've got a little bit of maths today. We'll see how this goes. I had planned to do this on our whiteboard. Because we're on the computer, we don't have a whiteboard, so I might just have to talk about it, and you all will just have to figure it out. So our inverse square law, we vaguely mentioned this last week, and that was that as a lamp is further away from the surface, then the light on that surface, or the light at any given point on that surface, will be reduced. That's not because the light is disappearing. You know, we're not getting less light out of the lamp. The light is not disappearing on the way between the lamp and the surface. It's just diffusing more, right? And we can illustrate this concept even just in our brains by thinking of shining a torch on a surface. As you bring the torch away from that surface, the area that's illuminated gets larger, but also less bright. If I put this torch right up to the surface, like this, then I'm going to get a small but very brightly lit circle on that surface. Does that make sense to everyone? You all know what I'm talking about, right? I can't do a physical demo, but I think you could all picture that in your head. Yeah, I'm looking for someone to agree with me here, or not, or disagree with me. Cool, thank you. I'll just take one person as your indicative of the class. So just any one random person can jump in and say yes or no. If everyone else is saying yes and you're a no, please jump in and say no. So the mathematical equation that governs this, why it works like this, I don't know. Somebody smarter than me has figured it out. But the mathematical equation is to do with the square of the distance from the source of lighting. So we haven't got what we would call a linear scale, which means that a linear scale would be if I doubled the distance from between the light source and the surface that's being lit, that I would get half the light, right? If I double the distance, get half the light. That would be a linear scale. This is not a linear scale. This is a square scale, or what do we call that? Any maths nerds? That's not a logarithmic scale. It's a shit. I can't remember the word. Anybody know what I'm talking about? You see the graph with the curve that starts out really steep and gets lower and lower as it goes along. It's not parabolic. I don't remember. I didn't do enough maths at high school, I suppose. Nevertheless, right, so what that means is that if I double the distance, I'm going to get, I'll still have, I'm going to have even less than half the light. This equation is based on the square of the distance. So we have a example here. Calculate the illuminance of a corridor if the total flux. Oh no, that's not an example of the inverse square law. Jesus Christ. Give me a second here, team. Sorry. Okay, we don't have an example of the inverse square law, so let me make one up in my head. If I have a lamp with a luminous intensity of 100 candela, and it is 10 times, and it's 10 meters from the source, my surface is 10 meters from the source, then my equation would be 100, that's my luminous intensity, divided by the distance squared. So that'd be 10 squared, so 100, it'd be 100 divided by 100. So that means that my illuminance on that surface is going to be 1 lux. So 100 is my luminous intensity divided by the distance squared, 10 squared. If I moved my light towards the surface from, let's say, 10 meters to 1 meter, I've put it 10 times closer, right? It's 10 meters down to 1 meter. If we do this equation, we'll see that the luminous intensity, 100 candela, is now divided by distance from source 1 meter squared, and 1 squared is 1, right? 1 times 1 is 1. So my luminous intensity has increased from 1 lux, or my illuminance rather, has increased from 1 lux to 100, because my candela is 100 divided by 1 squared is 100. So I've reduced the distance by 10 times, but I've increased the illuminance by 100 times. That's why we've got that. So I'm talking about with that squared scale as opposed to a linear scale. If you think about that the opposite way around, that means that if I have my torch shining on the surface, if my torch puts out 100 candela and I have that shining on a surface 1 meter away, then the illuminance on that surface will be 100 lux. If I move it 10 times further away, I go from 1 meter to 10 meters because of the square in that equation. That means that my illuminance on the surface reduces from 100 lux down to 1 lux. So by increasing the distance by 10 times, I'm decreasing the illuminance by 100 times. It's going to be distance squared is our important factor in that equation. Now there is a question in the test that uses this this formula. Obviously, you can come back to this and use that formula there. I don't think it's terribly difficult as long as you can substitute in the values into this equation. Use a calculator. You can't really get that wrong. Any questions on that? Am I making sense with this one? Cool. Ray's happy. Frey's happy. I'm happy. Okay, so we have an example here of calculating the illuminance. This equation here is only particularly valuable when we have uniformity of lighting. I guess we would use this equation if we set up our lighting in a way that is designed to be more or less uniform. If we think about our classroom from last week, we spent a bit of time looking at the lights there. We would call that uniform lighting distribution, right? Although, even though, if you close your eyes and think about that room, there is going to be at least some shadows in there. We're not going to get 100% uniformity. For the sake of simplicity, if we were designing that area, we would probably assume uniform light distribution across the whole area. Otherwise, it's just going to get way too complicated to try and figure out every individual light fitting, where that light's going to go, so on and so forth. So calculate the illuminance in an area. We've got 12 lamps, each are rated at 400 lumens each, so I can go 12 times 400 tells me the total light in that area, and the area is 12 by 6 meters, so I can multiply those to give me the surface area of the room to be lit. So the illuminance then will be the total flux, so that's my 12 times 400, the total amount of light that I'm getting, divided by the surface area. I mean, this is very simple, right? This is an easy calculation. That if you think about the light in this context as being an object, like if it was water or something, if I told you I had a volume of water and I was spreading it across a certain area, you should be able to tell me like how deep that would be. I mean, you'd have to figure out what the equation is, but it's the same sort of thing. That's all we're talking about here. A total amount of light distributed evenly across an area. What is the lux level per square meter? So it's going to be our total lumens, 12 times 400, times our total surface area in meters squared, which is 12 by 6. So 4,800 divided by 72 gives us 66.67. Very simple equation. Are we okay with that one? Cool. My man Solar Energy is happy. I mean, everybody happy. Okay, so this is where it starts to get a little bit more complicated. Our cosine law. So the inverse square law applies to areas where the source is perpendicular to the illuminated surface. If the surface is turned through an angle to the perpendicular, a correction of cos times the angle must be used. This little symbol here, that's 0 with a line through it, diagonal line through it, that's theta, I think. That's the Greek letter theta. So we use that to represent. If you haven't come across this before, it's just an algebraic symbol used to represent an angle. So we're talking about an angle here. So what do I mean by an angle? Well, can you guys see my video? You can see me physically, or can you only see the screen? I'll see my slideshow rather. Both. Okay, good. Okay, look at me for a second. Right. So if I have a light above a surface, then the light is going to come out of that surface like this, right? Like a cone. Oh, that's really weird. I just got a notifications popped up on Teams here saying that your spotlighted video won't be recorded, which I guess means that if I start doing stuff and you guys are watching me, it's not going to record that. It'll just record my screen. So I guess if somebody else is watching this, they may not be able to see me if you're watching this later. It's really strange that that's just popped up as I asked you guys to look at me and asked whether you could see my video. It like makes me feel like Microsoft Teams is listening to me. That's really weird. I feel kind of creeped out by that. Anyway, so we have a light and it's shining down on a surface, right? So it looks like this. So that inverse square, that is, it's a little bit tinfoil hat there, Ray. I agree with you, but it's kind of weird that I literally just asked if you guys could see my video because I wanted to use my hands to illustrate a point, and then Teams has just popped up a message saying your video is not being recorded. Like it's recording the meeting, but it's not recording my webcam. Definitely fucking listening to me. Anyway, so the inverse square law, if we go back a couple of slides, where is it? This one here. So that's talking about the illumination directly under that light. So if my light is at the top here and it's shining down like that, we use this calculation here to calculate the illuminance on a point directly underneath that light. That's what it means by perpendicular, right? On a straight line down, or a right angle, if you like, at a right angle to the surface. So there's my surface, right angle, pointing straight up to the light. So if you were to ask to calculate the illuminance on the surface directly below the lamp, this is the one that you're going to use, this one here, the inverse square law. But, and that will also be the maximum illuminance, right? So if you get the question that says, what is the maximum illuminance? Then you're going to use this rule, because it will never be, no part of that surface will be lit more brightly than the point directly below the lamp. Is everybody with me so far? Okay, good. So then we can imagine then that as the light spreads out from that lamp, that the points on the outside of that, if we think of the light coming out in a cone, it won't be perfect, but if you think of the light coming out in a cone onto the surface, then at the edge of that cone, that's where I'm going to see the lowest amount of light. Does that make sense? Yeah, I'll take it. I assume we all agree with that. Right, so so at the edge of the cone, I'm going to get the lowest amount of light. If we could have a light that, you know, only shone on a specific area and there's nothing outside it, then we'd be talking about a cone of light, and then on the outside, after that, will be darkness. Outside my cone would be darkness. Therefore, it makes sense that the outer rim of my cone shining on a surface is going to be where I get my lowest amount of light. So again, if you're asked to calculate the minimum illuminance, then that's what we're looking at. We're looking at the outer edge of that cone. So mathematically then, we have to add in that angle. So again, if we're talking about our cone going down, if I'm looking directly downwards to a point directly below the lamp, then there is no angle. If I'm looking at the edge of that cone, then my angle is this angle at the top, right, where it's shining down like that angle there. I hope me waving my hands around here is making sense. Yeah, so that angle in there is going to be the angle that the light is falling at. And the greater that angle is, the lower the illuminance would be. So if I had a cone that looked like this, then I'm still going to get most of my light falling on the edge of that cone. If my cone looks like this with a big angle, then my light is going to be much, much more diffused, and therefore at the edge of my cone, I'm going to have much less light than I did before. So we need to be able to figure out how to work out illuminance using the angle that the light is falling onto that surface. Okay, is everyone with me? We kind of accept that basic principle. Say yes if you agree. Yeah, okay. So Ila gets it. I mean, so Ila gets it, but he's smarter than most of you. So does everybody else agree with Solar? Oh, Roy does. That's good. You think I'm joking, Solar, but you might be the smartest person in the class. I think most of the time you're just making fun of the rest of us. Yeah, I agree, Narendra. He's real smart, eh? He keeps it secret. Anyway, okay. Right, so it seems that most of us agree with that. Okay, so how are we going to calculate that? Well, we have this formula here. So now our illuminance. Now, if we look at this, we will see that that's almost the same formula as we had before. If we go back, luminous intensity, so that's the light output candela or candle power. So is our light intensity divided by distance from the source squared. Cool. So that's our formula if we're looking directly below the lamp. So if we come back to this one here, we'll see that we still have the same thing. We've got luminous intensity in candle power, candela, and we have distance from source in square meters. Distance from source squared. But now we've added in this little bit here, cos theta. So the cosine of the angle. Now that's really easy to do in our calculator because if we know the angle, then we just add, you just push the cos button and then it's going to come up with cos on your screen and it'll come up with brackets and you put whatever the value of the angle is into those brackets. So cos times the angle. So it's the same formula, it's the exact same formula. We're just adding in that angle there. We're multiplying our luminous intensity by the angle. So that gives us that's how it calculates the difference between light falling directly down there and light falling out to the side. The luminous intensity of the lamp is still the same, but the angle on which it's striking the surface reduces the illuminance. So we add in that angle there. Now, the only other thing to think about here is that the distance from source is different, right? So if I were to do both of these formulas, both of these equations for the same lamp, but one I wanted to measure the maximum illuminance, so that would be where I'm directly below the lamp, and I want to measure the minimum illuminance, so that's out on the edge of my cone, then the distance from source changes, because the distance from here, the lamp, directly down to the surface of, let's say it's a table, is different to the distance from that lamp to the edge of the cone where it strikes the table out here. And that's a right angle triangle, right? That's a Pythagoras triangle. Is everybody with me there? We understand why that distance changes. Even though the distance from the lamp to the table doesn't change if it's the same lamp. If I said I put that lamp 1 meter above the table, that's 1 meter from the lamp directly down to the table. The distance from the lamp to the edge of that circle is different. That's a larger distance. That's a Pythagoras triangle or a right angle triangle. That's the hypotenuse of our triangle. Does everybody know what I mean by that, like Pythagoras and right angle triangles? Does anybody not know what I'm talking about? I know it can be an intimidating thing to just stick your hand up in this context and go, no, I've got no idea what you're saying. Please explain it further. But I don't care. It's no judgment from me. So if you don't know, I'd rather you say I don't know, and I will explain it further. Then everyone agree with me and actually not know what's going on. So if you don't know, be brave. I'll give you about 20 seconds to go, no idea what you're talking about. Okay. All right, we'll move on then. Looks like everybody's okay with this. All right, so here are our equations here. This is what I was kind of waving my hands around illustrating. So we've got our light source here, and at the bottom here, we have our illuminated area, which bizarrely we've colored dark on a light background, which like is the opposite of what we're trying to illustrate, but okay. So we have a circle of light here, and we need to calculate the illuminance on 2 points on the circle. One is the center, directly underneath the lamp, and one is at the edge of my cone, or the edge of my circle of light out here. So we've seen the formulas. Those formulas are fairly straightforward. On the first one here, this looks different to what we saw before. It's the same thing. So E here represents the illuminance, and it says max down there, so that means the maximum illuminance. I being the lighting output, that's our candle power, and d squared being distance between the illuminated point and the lamp itself, squared. So it's the same as the formula we saw before, I over d squared. So that would be 200 candle power. It says at the top, a lamp emitting 200 candle power in all directions below the horizontal is mounted 2 meters above the center of the circular table, 3 meters in diameter. Calculate maximum and minimum illuminances on the surface of the table. Now, you'll have this exact question in the test. I'll warn you now. So this is important that you understand this. If you don't understand this, I don't think that you're going to be able to just go back to the slide and substitute the values in. You do actually need to understand what you're trying to do, otherwise it's not going to work. So I would very much appreciate feedback as we go along from people that we're actually getting this. Okay, so let's go back to our first formula then. So my maximum illuminance is going to be this point here at the center. And the formula I use is the illuminance divided by distance squared. Now it says here, up here, that my light is mounted 2 meters above the table. So that's the distance between my lamp and directly downwards to the table. So 2 meters, right? It says it right there, 2 meters. And the candle power of the lamp is 200. So it's 200 divided by 2 squared. 2 squared, 2 times 2 is 4. So 200 divided by 4, 50 lux. It's pretty straightforward. That one, yeah, again, you don't need to understand too much about that. You just put those values in. It just tells you what the candle power is and the distance. You just use this formula here, substitute it in. So what this is telling us then is that my illuminance on this point here should be 50 lux. What that means in practice is that if I go and buy a light meter and I stick it on that point, it should say 50 lux on that point. Now, where it gets a little bit more complicated is measuring the illuminance out on this point here. So because we have this angle, we have to factor that into our equation, because the bigger that angle is, the greater reduction of light levels that we're going to get. So here is our formula over here. So our minimum illuminance, this is a minimum illuminance. Minimum illuminance is because we are right out on the edge of the cone, or in fact, in this case, we're out on the edge of the table. It does say here that the lamp is emitting 200 candle power in all directions, so presumably we're emitting light out in this direction here, so there'd be even less light over here if I wanted to measure that, but it's talking specifically about the table. So our minimum illuminance on the table then must be right on the edge. So I've still got 200 candle power. If we look at the formula here, it's going to be 200 candle power times cosine of the angle. Now this is my angle here. The angle is the angle between the perpendicular, straight down from the light source to the table, and the line from the lamp to the point that I'm measuring. So that is the angle that we're looking for. Now in this case, that angle is 36.87 degrees. So it says there, 36.87 degrees. Yes, Maxwell, we are going to use Pythagoras theorem for lighting. I know, it's a horrible trick, isn't it? Well, in fact, we're going to go a step further, because what I'm talking about now is we actually want to know that angle. Pythagoras theorem will tell me, actually, let's go to the Pythagoras first. So in this formula here, I need to know that distance, right? I need to know d squared is part of my formula. Now, as I said, the lamp is 2 meters from the surface of the table, but the distance from that lamp out to the edge is going to be a different number. It's not going to be 2 meters. If you just assume 2 meters and you use 2 meters in this equation because it says that the lamp is 2 meters above the table, you're going to get this wrong. It's greater than 2 meters because we can see that triangle here. That's a Pythagoras triangle, right? And the triangle, the way we work out that distance is using Pythagoras's rule, which is a squared plus b squared equals c squared, or the square of the hypotenuse is equal to the square of the other two sides. So we go 2 meters squared plus 1.5 meters squared equals this distance here squared. So the easiest one is the 3, 4, 5 triangle, which many of you will come across before. If I had 3 meters on the bottom, 4 meters here, that means 3 squared is 9. 4 meters here would be 4 squared is 16. 16 and 9 equal 25. So that means that this line here, or the square of this line here, is 25. So if I do the square root of 25, it gives me 5. So if I have a triangle, right angle triangle with a distance of 3 on one side, 4 on one side, then the distance on the third side, the hypotenuse, the longest side, must be 5. And in fact, this triangle here is a 3, 4, 5 triangle. It's just halved. So I've got half of 3 on the bottom here, 1.5, half of 4 on the side, it's 2 meters, which means that my length down here must be half of 5, 2.5. And in fact, if you look over here, that is exactly what we've done. Now, if we were in class, I'd probably throw some right angle triangles on the board and get you to work out, use that Pythagoras theorem. I'm going to assume that you guys can all do that yourself. If you're struggling with it, if you come to do the test today and you struggle with it, flick me a text, let me know. However, you'll find calculators online for this. If you go online and you type in, go onto Google and type in Pythagoras triangle calculator, you'll find one. And you'll just be able to enter the values and it's going to tell you the answer. Are we cool with that? Yeah, if you don't understand Pythagoras theorem, if you don't know this stuff, if you didn't do it at high school, or you don't remember how to do it, Google it. Google's your friend here. Like I said, you can find a calculator, but you'll find plenty of stuff online that will explain it to you. 100% chance that if you just jump on Google, you will find lessons or explanations of Pythagoras theorem. You could do your own little course on Pythagoras. Narina, okay, yeah, can you explain the d squared again? This number here, d squared. Is that what you're talking about? Yeah. So for the angle, do you mean so how to work out this size here, this side? Or do you just mean d squared in general in both of these formulas? Where does the 2.5 come from? Cool. Good question. Okay, so this is a Pythagoras triangle. This is a right-angled triangle. And a right-angled triangle, we can work out the length of the longest side by using the length of these two sides here. The 1.5, actually, I didn't explain where that comes from. If we look up here, it says the table is 3 meters in diameter. So the diameter of a circle, if you don't know, is the distance from one edge to the other. So it's the distance all the way across that circle is diameter. And so we're talking about from the center out to the edge. So that distance there must be 1.5 meters. That's half of the diameter. So Pythagoras theorem again tells us that the length of the hypotenuse, that's this side here, is called the hypotenuse. The square of that side there is equal to the sum of the square of the other two sides. So if I get 2 meters squared, that equals 4. If I get 1.5 squared, let me grab my calculator. (1.5 squared is 2.25. So I'm going to go 4, that's 2 squared, plus 2.25 squared. 1.5 squared, which is 2.25. So 4 plus 2.25, which gives me 6.25. And then I want the square root of that. So 6.25 is the square of this side here. Because again, Pythagoras theorem tells us that the square of the hypotenuse is equal to the square of, or the sum of the squares of the other two sides. So the square of this side plus the square of this side equals the square of this side. So we just worked out the square of this side plus square of this side is 6.25. So I take the square root of 6.25. And unless I'm a complete gumboot, that should be 2.5. Yeah, cool. And we have it there. Does that look backwards? Sorry. Square root of 6.25 is 2.5. So that is the length of that side there. Does that answer your question, Narendra? Yeah, okay. So if anybody else is still struggling with that, if you've never come across the Pythagoras theorem before, and you're like, what is this guy on about? Just scroll up to Maxwell's comment. He has written, we're using Pythagoras theorem for lighting. Highlight Pythagoras theorem, click copy, paste it into Google, and that will explain everything for you. I say go up to Maxwell's comment because it looks like he spelled Pythagoras right, and I don't know how to spell it off the top of my head. And if you've never come across Pythagoras theorem before, you probably don't know how to spell it either. So he's written it up here for us: Pythagoras. And just as a little aside, if that seems like a strange word, it's the name of the guy that discovered the rule. His name was Pythagoras. He was a Greek dude a long time ago, and he figured out this rule about triangles. So we call it Pythagoras theorem, named after the man himself, old Dave Pythagoras. Okay, so now we get a little bit more complicated. Maxwell, I apologize, mate, if you thought Pythagoras theorem was ugly. Now we're going to do some genuine trigonometry. So, shit, this one's going to be tough. This is going to be tough over a video call. So we need to work out what this angle is here, because we don't know. We need it for this formula, right? I said that before, that we're going to need to use the cosine of the angle to work out our illuminance out on this edge. So the first thing I need to do then is, yeah, oh God, I know. Yeah, trick. Look, if it makes you guys feel better, or this won't actually, it might make you feel worse. We're going to do a shitload more trigonometry next year, like heaps of it. You're going to get intimate with trigonometry, and you're going to learn to love it. By God, you'll learn to love it. So to take this as a small baby step introduction into our trigonometry. But on the plus side, I'm almost certain that by the time you finish this course, you will understand trigonometry and you'll feel more comfortable with it than you ever did in high school. I don't know whether that's because as grown-ups, our brain power, ability to understand weird concepts gets better, or because I'm an amazing teacher. Almost 100% definitely the first one. Maybe a bit of both, right? So we're going to work out what that angle is. So we're going to use the trigonomic function to work out an angle, which is, we use SOHCAHTOA, right? So SOH there, SOH, is sine equals opposite over hypotenuse. Ka is cosine. The cosine is equal to the adjacent divided by the hypotenuse. And TOA is the tangent of the angle. Tan is equal to opposite over adjacent. So what do those words mean? Hypotenuse, opposite, and adjacent. Those are words to represent the lines on our triangle, the sides of our triangle, in relation to the angle that we're trying to work out. Okay, so we already discussed with the Pythagoras theorem that this side here, the longest side on my right angle triangle, if you didn't know this trigonomic this trigonometric calculation only works for a right angle triangle. That means a triangle with an angle of 90 degrees down here. Excuse me. So for a right angle triangle, as we said in the Pythagoras theorem, the longest side here is the hypotenuse. Now, I could use trigonometry to work out this angle here, that one there, or this angle here. I don't need to worry about this angle here because that's a right angle. It's 90 degrees square. So we already know that one. So in relation to the angle that we're trying to work out, we give the sides names. If I'm looking at this angle here, this side here is the opposite. Why is it the opposite? Because it's opposite to the angle. If we have a triangle, then every angle will have a side that is opposite to that angle. And that means that neither of the sides that are touching that angle, it's the third side. It's not either of the triangle. It's not either of the sides that is touching that angle. You can see here, if we're looking at this angle, then that side there and that side there are touching that angle. This side here is not. So that's my opposite. This side here is my hypotenuse, which means this side here is my adjacent. Adjacent, just English lesson, if you're not aware, adjacent means next to or beside. So adjacent in this context then means the side that is next to the angle. And this, again, this is all in relation to the angle that we're trying to work out. In this case, we're working out this angle here. So this one here then must be my adjacent side. Why is it not this one? This side's also touching the angle. Well, that one's the hypotenuse. That's already got a name, so we're not going to worry about that one. We're just thinking about this one here. That's my adjacent side. So, given what we know then about this triangle, I'm given the adjacent side here. I've got that value. That's 2 meters. I've been given the value of this side. That's 1.5 meters. That's the opposite. So I know the adjacent side. I know the value of the adjacent side. I know the value of the opposite side. Therefore, I can use the function TOA. The tangent of the angle equals opposite over adjacent. TOA. Tangent equals opposite over adjacent. I have the opposite. That's this one. I have the adjacent. That's this one. Therefore, I can use TOA to work out the angle. Now, the function in the calculator, I'm going to type this into the chat so you can see it. The function I'm going to use in the chat, TOA is generally used for us to find the value of a side if I already know the angle. So I've got 3 variables there, right? Tangent of the angle, opposite side, and adjacent side. So in algebra, anytime I have 2 variables, I should be able to work. If I've got 3 variables in an equation, tell me the number of 2 of them, and I should be able to work out the third, right? The most simple form of that would be if I said x equals 10 plus 5, or 10 minus x equals 5. If I said to you 10 minus x equals 5, all of us can work that out in our head. 10 minus x equals 5, x must be 5 also. That's easy, right? Because I've got an equation with 3 numbers in it. I've given you 2, you can work out the third one. So that's what we're doing with this trigonometry. In this case, we're using TOA. Tangent of the angle equals opposite over adjacent, or opposite divided by adjacent. So now I've told you what 2 of those numbers are, the O and the A, 1.5 and 2. So now we just have to work out tangent of the angle. Now, normally we would use this equation to work out what the angle is. Sorry, no, we would use it to work out what one of the sides is if I already knew the angle. So I could say tan, in this case, we're told what the angle is. Tan 36.87 equals 1.5. That's the opposite divided by 2. So if I had, if I didn't know what the value of the opposite side is, if I just knew the angle and the adjacent side, then I would use this equation to work out what the value of the opposite side is. But we're going to use it to work out the angle, which means we need to use the inverse tangent function. Okay. So that's the formula we're going to use in our calculators. Tan to the -1 times opposite over adjacent. In this case, my opposite is 1.5 and my adjacent is 2. It's directly off the slide there. So I can substitute those values in there. I'm using the little arrow, so I've got the tan with the arrow up, -1. That means it's to the power of -1. You should be able to find that on your calculator, to the -1 function, or to the power of function, and we type -1 in there. So we're going to go tan -1 brackets opposite, which was 1.5, divided by the adjacent, which was 2. Just like that. Type that into the chat. So if you look at what I've written in the chat there, that is the formula you're going to need to use in your calculator to work this out. And like I said, this question is in the test. It's not the exact same. It has different values, so you're going to need to figure this out. So what I want you to do now, on your computer or your phone or your calculator, do this formula. Tan to the -1 brackets 1.5 divided by 2. If you do that, should give you the value 36.87. I want everybody to do that. I want you to just type in the chat that you got that you did it and it came up with 36.87. I've got it on my calculator here. When I'm holding my phone up to the screen here, it looks backwards to me. Is it backwards to you guys? Or can you see what I've got there? No, it's fine. Okay, cool. Okay, so you should be able to see there, that's the formula that I've used, tan to the -1, brackets 1.5 divided by 2, and the answer it's given me is 36.86989765, or 36.87 if we round it. We'll get through this team and we'll take a break. So 10 more minutes. Okay, so a few of you have said, yeah, you've got that correct. I'm assuming the rest of you have not done this. You're just sitting there watching, or actually maybe you're watching TV and this is on in the background. That's fine. When you get to this in the test, remember that you didn't do this when I asked you to, and then don't bug me about it, because, like, honestly, if you don't want to listen, then whatever. I don't mean that in a mean or nasty way, because if I was in your shoes, I probably wouldn't be listening either. So what I mean is, when you get to the test and you can't figure this out, go to Google and find a lesson on how to work out trigonometry, because I'm not going to spend my time to explain it again. You're on your own. Okay, so we've got that, right? So we've worked out our angle. So now we can put that in the formula. Here's my formula here. The minimum illuminance, as in the luminance out on the edge here, is going to be equal to I, which is our illuminance out of the lamp, which was 200. So I times cos of the angle, so which is, again, just like we did in this one, we're going to use cos instead of tangent. Let's not go into why. Let's just accept it. Otherwise, we'll spend another half an hour talking about this. And that's going to, so cos of the angle divided by distance squared. So the values here, 200, that's my candle power of the lamp, times cos 36.87. So 36.87 was the angle. So I just type into my calculator cos times cos 36.87. I'm just going to do this on my phone again so I can show you. I'm not using cos -1 as I did before. I'm just using cos. And then on the bottom line, I have got 2.5 squared. It's my distance squared. And again, if you've already forgotten, why is it 2.5? Because that hypotenuse on that triangle is 2.5 meters long. And so here's what I've got here. 200 times cos 36.87 divided by 2.5 squared gives us 25.5999657. Everyone can see that okay? Good. Okay. And then, in fact, if we look here, is our answer, 25.6. Cool. Job done. Okay. I think I've said enough about that. How are we feeling about it? I know this is unfortunately a difficult concept to work out or to understand on a video chat. If we were in class, I'd scribble some examples on the board and I'd wander around and make sure you're doing it right, but I don't have the ability to do that here. I was half joking when I said before, if you don't get it, don't ring me. Yeah, don't ask me to redo the lesson for you because you weren't listening. But if you do need help later on, let me know. I have videoed this, and it will be in our Teams on Microsoft Teams. You should be able to go into videos. You should be able to watch back everything that I just said if you're struggling with the answer. So, is everybody happy for me to move on from here? Okay. Okay, so this next slide here, explanation on mathematical term, got 2 plus j 1.5. If you go back here, they've used that 2.5, 2 plus 1, excuse me, 2 plus j 1.5 arrow, 2.5 meter, 36.87. Look, it's another way of doing the same thing. It's just a slightly different way of looking at it. I'm not going to read this, and I'm not going to explain it, because I've explained it to you guys the way that I do it, which I think is the simplest method. However, if you want to read that yourself, use the method that they're talking about there and work that out. That's fine. But yeah, if I'm honest with you, I'm not even exactly sure what they're talking about in this slide. So we'll use the method that we've got. Again, I cannot emphasize this enough. Trigonometry, Pythagoras theorem, we don't use them every day, but you know they're common as hell. So if you're struggling with any of that stuff, there's just untold resources on Google. There are people there that are much smarter than me who will explain this in much better ways. So if you can find a YouTube video that'll probably tell you how to do trigonometry and Pythagoras in 10 minutes or less. And so as we flick through the slides here, we've got a slide on the how we worked out that hypotenuse. That's Pythagoras theorem there. A squared plus b squared equals c squared. 2 squared plus 1.5 squared equals 6.25. Therefore, the hypotenuse is the square root of 6.25 equals 2.5. So that explains how we got that 2.5. This is how we find the angle. As I just went through, the angle equals tan to the -1 times the opposite over the adjacent, 1.5 over 2, which gives us 36.87. And that is the end of that slideshow. How are we feeling? Any questions? No, we're happy? Okay, so I've just unlocked that test, so you can have a crack at that. Oh, okay. Yeah, I'll come to you in a second, Ray. All right, so I've unlocked the test, so you can go and have a crack at that at any time now. We'll take a break now for about half an hour. So if you wanted to jump in and have a look at that test now, that's fine. But before we go, I'll answer Ray's question. So saying there, light diffusion, why don't we see that with a spotlight? So do you mean why are spotlights not diffused? Why do they just shine directly? Is that your question? Or yeah, why do we not use diffusers on spotlights? Is that what you mean? Have you got a microphone, Ray? You could jump on and explain what you mean.
Can you hear me?
Yep.
So one time when I was younger, I saw a police helicopter flying over, and I saw the spotlight, but
Yep.
it was just in a straight beam of light. I didn't like the light didn't kind of fade
it didn't
as it
spread. Yeah. Okay.
That's something
So-
I've thought about.
Yeah, it's a good question. So the inverse square law tells us that that there will be that diffusion and distance from the light source squared, blah 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 blah. The difference there is that, you know, if we looked at that example on the slideshow where we had that quite a large spread from that lamp, which was unshaded, right? The lamp was unshaded, so the light's going to travel in every direction, and then obviously according to the trigonometry that we just did, and the inverse square law and cosine of the angle, blah 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 blah, that tells us that the further it goes out on an angle, the less light that there will be. So what you're seeing with a spotlight like that is it's probably from the light source. It'll have a I don't even know what the word would be. Tube, let's say tube. We have a tube coming from the front of that lamp that does not diverge at all. It will not be a cone. It'll just be straight. And then behind the lamp, we're likely to see a mirror or a reflector, like the reflectors that we saw in our lights in our classroom, except it'll be like a silver reflector, right? So what we're trying to achieve there is that every bit of that light coming out of the lamp is all heading in the same direction. So any light that's going backwards is going to hit that silver reflector, and it's going to be reflected down. Why we have the tube out the front is that so we're not getting any divergence of light out to the sides. It's all going to go straight down that tube, and therefore everything that emerges from the end of that tube is all heading in one direction. Now we're getting into some like kind of weird theoretical physics here, I suppose, but if you think about light in this context as being a thing, like a particle, let's say it's like water out of a hose. If you put all the water coming out of that hose in exactly the same direction, then it's going to keep traveling in the same direction. So in this case, our photons, our light particles, all coming out of that tube with a reflector in the back, all heading in one direction. There will be some scattering. As it comes down that tube, some of the light's going to hit the sides and then it will emerge on an angle out of the end of that tube. But if you set it up right, then the majority of that light should be heading in one direction only. Just like if you had the hose and you made sure that everything was coming out in the same direction, then it's going to keep going in the same direction. The only reason that that water out of a hose will eventually diffuse is gravity, basically. So light's not really affected by gravity. So it's just, I mean, light is affected by gravity, just in case you're wondering. If anybody's going to take this lesson of physics away, light is affected by gravity, but not in any sense that will affect us. So we can assume no effect of gravity. So light will come out of that tube, it's all heading in the same direction, and therefore it should stay going in the same direction. If all of those photons are going in the same direction, like particles of water coming out of a hose, and they're not affected by gravity, then they should all strike the surface in the same spot. So we should get a relatively small illuminated area when it actually strikes the surface. And so we're actively discouraging any sort of diffusion. We're keeping it all going in the same direction. And if we do that, then, you know, light is a weird thing. So it should should give us a single point of illumination at the end. Again, as the distance increases, then that randomness that we have in there and that small amount of diffusion will increase, and therefore that cone where it strikes an area is going to get bigger. But again, if we've done a good job of directing the light in the right direction from the start, then it should still be relatively small. And I think that answers your question. Does that answer your question?
Yeah, it does. Thanks, Dan. Appreciate it.
Yeah, sweet. That's a good question, though. Yeah, when you think about it, it does make you wonder why is it not spreading out? But yeah, I guess you point your photons in the right direction, and they'll just keep going in that direction. So there you go. Cool. Thank you for that one. Appreciate that question. Anything else from anyone else? Okay. Let's take a break here, right? Let's take half an hour. You can all go and have a cup of coffee or a sandwich or whatever you need to do. So we'll start again at 11:15. I'll just leave this video continuing. If you're watching this in the future, you're watching a recording of this, you're going to need to skip the next 30 minutes because it's just going to sit here recording. I'm going to turn my camera and microphone off, so because you guys don't need to watch me have a coffee and pick my nose. And then we'll jump back on at 11:45. I'll see you then. Cheers. I'm back. We'll give a couple of minutes for everyone to jump back in, and then we'll crack on with the next thing. Can everybody hear me again? Cool. All right, let us carry on. Okay, a little bit of housekeeping. So just looking at our marks for the tests in this module so far. And I can see that first. So the two, how many tests did we do last week? Four. Does that sound right? 4. Yeah, so it looks like we've got about half of us have done all of them. The rest of us have done some of them. And a couple of people who've done none. I've talked before about the importance of keeping up to date with our tests, right? Again, we're going to have that point when we get to our capstone for this module, that you need to have all of those tests complete. I know that there's, you know, as long as you hit that deadline, everything should be fine, but I'm becoming increasingly worried that people will not. And I mean, I find it annoying and frustrating from in the sense that you just simply refuse to do what I ask you to do. But it's also concerning that that we're going to end up with a situation where either I have to play the bad guy and tell you that you can't do that test, or I'm going to have to again run around after people and make sure they do them. So I've decided that I will put a due date on tests, which means that I'll make it Sunday. So the end of the week in which we do each topic, I'll put the due date as midnight on the Sunday, which means that after midnight on Sunday, you'll no longer have access to that test. So once I unlock it, you've got until that Sunday to complete it, and after that, it will turn off, and you will not be able to do it anymore. So I'll retrospectively put that on all of the current tests as well. You just need to get them done, team. They're not optional. It's not a hardship. This is part of the course. You've got to do those. You've got to do those quizzes. I'm pretty bored with talking about it, to be honest with you. So all of the tests will have a due date. Once that hits that due date, you will no longer be able to access it. And then after that, well, I guess bad luck, unless you want to come and plead your case to me, in which case we'll have a discussion about it. Then I recommend that you just get them done before the due date, please. Does anybody have any issues with that? Think I'm being unfair for any reason? Go through while we're sitting here and add those due dates. Yeah, so for those people who haven't done any of the tests so far from last week, that means that between now and Sunday you've got 8 potentially 8 tests to do, which is outrageous. There's absolutely zero reasons why that should be happening. Okay, give me a moment to just go through and add these due dates so I don't forget. Oh, come on, Jake. Why do you have to put a fly in the ointment of my plan? Yes, actually, that's an unintended consequence. Don't worry. I will fix that. What I will do is put in a practice test, which will allow you to do a test that would have 20 random questions, the same as our capstone. But yes, it would mean that. Unfortunately, that is the stance I'm going to take because I'm just, I'm really over this chasing people around. Again, we've got, for this module, we've now got 6 tests unlocked. And as I said, there's some people who've done none of them. And I don't think I'm being a dick here, because those people that have done none of them are the same people that continue to fall behind in every other module. And as I've said before, the people that are creating additional work for me because I have to run around like I'm their mum and say, oh, can you please do those tests today? It's lame. It's lame. Take responsibility for yourself, for Christ's sake. Be a grown up. If you want to be on a grown up course, act like a grown up. All right, enough whinging about that crap. Let us move on to the next topic, incandescent lighting. So this one should be a little bit more straightforward than the last one. There's no maths in this, so we'll bang through this. I reckon it'll take about a bit over an hour. So so we should get through this by lunchtime. We'll stop and have lunch. And then we will, I think we'll carry on after lunch with the next topic. We won't finish the next topic today, but we'll make a start on it. We'll see if we can get about halfway through it. The next topic after this one is, this one is incandescent lighting. So the next one after this is going to be gas discharge lighting. So gas discharge lighting is probably got the most stuff in it of the remaining lighting topics. So we'll do half of that one today and half of it tomorrow to give our brains a bit of a break, because it is quite a dense topic if you do it all in one hit. Can everyone see the slideshow, the incandescent lighting slideshow? Magnificent. Here we go. So, what is incandescent lighting? Well, we've talked about this before. We should have a rough idea of what we're talking about now. And here it is here. When you pass an electric current through a filament lamp, a wire, it glows white hot and becomes a source of light. Ordinary wire does not last very long. It hasn't the mechanical strength to withstand the high temperatures. When exposed to the air, the wire becomes oxidized and even weaker. A better filament wire is made by using tungsten, which has a very high melting point. It is then enclosed in a sealed glass bulb from which the air is removed. It's just pretty basic, right? So this is our oldest form of lighting, or oldest form of electric lighting. And the principle is exactly as described there. It's very simple. I get a piece of wire. It's going to be skinny. It's going to be a skinny piece of wire. If you look into an incandescent bulb, you'll see that the filament in there is like it's the thickness of a hair or something like that. It's very small. Why does it want to be very small? Because we need to create some resistance there, right? So we reduce the cross-sectional area to create some resistance. And when we create resistance, we create heat. As we pass a current through something with high resistance, it's going to heat up. And in this case, we're heating it up so much that in fact glows. And the glow that we're getting is what's producing our light. If you go back to the earliest days of electric lighting, that's exactly what it is. We just get a bit of wire and pump enough current through it for it to heat up red hot and create some light. Over the years that has developed, and I think we've talked about this before, and we've got it on that slide there, that we've experimented and changed the metal that we're using and found something that has a very high melting point, which means that we can heat it up really hot, produce a lot of light, and therefore have a reasonably bright bulb. And in addition to that, people have figured out that having air in contact with the tungsten filament as it's glowing creates that oxidization process, right? So that degrades the filament and therefore reduces its lifespan. So removing the air, vacuuming out that bulb, dramatically increased the lifespan of the filament and therefore lifespan of the light bulb. So I think back in the day, you were getting literally a few hours of life out of a light bulb. So these would have been luxury items that rich people had, and you would certainly you'd be looking to conserve the life of your bulb and use it in the minimum amount possible. Obviously, over the years, additional technologies have been developed to produce light, and therefore, particularly with the advent of the compact fluorescent lamp in the last 20 years or so, and then the LED lamps in the last 10 years or so, means that the incandescents are becoming increasingly rare, and they will become redundant in our lifetimes, as I've probably said 100 times before. Interestingly, here's a little aside for you, and if this does interest you, I recommend you go and look it up. But I believe that the oldest incandescent lamp that still works is it's at a fire station somewhere in America. It's like a porch light or something like that, and it's been going, they reckon, for over 100 years. They don't turn it off. Like they've sealed up the switch, so you can't turn it off. It just sits there and glows, and it is producing a very small amount of light these days because it's degraded to the point where it's no longer particularly bright. But it's a little bit of a historic curiosity, I guess, an anomaly in that there's a 100-year-old bulb somewhere. So it's literally been burning away for tens of thousands of hours, way beyond the normal expected lifespan for any incandescent bulb, and certainly way beyond the lifespan for any incandescent bulbs that were produced at the time that it was made. Nobody knows why. Nobody knows why that bulb doesn't work. And I think it seems that the consensus is about, oh, there you go, installed 1901. Have you just looked that up yourself there, Maxwell? Or do you know about it already? or is mum standing behind you telling you? Yeah, I mean, you guys know that I'm a bit strange, and that kind of stuff appeals to me. But there you go. So it's 119 years old, and nobody knows why it still works. So there's a bunch of people who just want to keep that thing going for as long as possible, and there's a bunch of people who can't wait for it to burn out so they can pull it to bits and figure out why it's like that. But there you go. So it's a live stream. Oh my God, you guys are almost as bad as me. Okay, I've got to click this. Give me a second to live stream of the 120-year-old bulb. There you go. Oh wow, that is fantastic. Okay, hang on. Let me. Can everyone see that? I did not know that there was a live stream for it. That's amazing. So there is the. You can't see that? The screen that I've just shared is not working. Okay. Okay. Oh, let's try this instead. Does that work? Now, don't click the link. We should all just sit here and I'll screen share and we can just all watch the bulb. So there it is, 120-year-old incandescent bulb. In fact, you can see that the fitting in there is obviously 120 years old as well. I'm kind of surprised that that hasn't fallen apart. I suppose they've gone to some pretty extraordinary lengths to protect, obviously, just not just the bulb, but the fitting and the wiring itself. I mean, even looking at that raises so many questions to me. I wonder at what point somebody realized, shit, this thing's been going for a lot longer than it should. Like 2 years, 5 years, 10? Is it 50, sitting there for 50 years, and one day someone looked up and went, see, that bulb's been there for a long time. There you go, the longest continuously lit incandescent bulb, 120 years old. There's just no way. There's no scientific explanation that everything about that thing tells us that it should have blown a long time ago. We say a long time ago. If it's been there since 1901, it probably should have blown in 1902. But here we are in 2020, and the damn thing is still going. How cool is that? Okay, back to our slideshow. All right. Okay, so the two things we talked about there, the tungsten metal, which was used because it has that high melting point, and vacuuming out the bulb itself, and removing the air so that there's no oxidization going on. Removing the air also helps us with the heat, as heat doesn't travel particularly well through a vacuum. Well, you'll get no convection heating in there because the air inside can't get hot. There is no air, so you only have radiated heat out of it. Which is also going to help to protect the filament. And there's a pretty picture of what a filament would look like. It's just essentially a coil of very fine wire suspended between two electrodes, which is going to be your phase and your neutral. It's just going to pass a current between the two. And here's our picture of a bulb. I'm sure we've all seen a light bulb before. There's nothing exciting there. Is our filament in the middle, again, very tiny, about the width of a human hair. It says a vacuum or noble gas, so occasionally you'll have gases put inside the lamp rather than a vacuum. The light from an incandescent filament lamp is made up of all the colors of the spectrum from violet to red. Not all sources of light show all colors, as you'll see with gaseous discharge lighting. So this is one of the primary advantages of an incandescent light, other than the simplicity of it, I guess, and therefore cost effectiveness in terms of the purchase price of a bulb, is that it has all of those colors of the spectrum, and that goes back to what we talked about in the last topic around color rendering. So in spite of the fact that a incandescent bulb has quite an orange light compared to certainly daylight and most other types of lighting will certainly be whiter than an incandescent. So in spite of that, even though it's quite orange, we'll still get pretty good color rendering. So you can see the true colors of most things under an incandescent light, and that's a real huge advantage. As I said in the last module, it's not something we think about often, but poor color rendering is immediately noticeable. When you're under a lamp that has very bad color rendering, you know about it immediately, and it's ugly. It's a horrible thing. So factors that affect the lifespan. The average life of an incandescent lamp is about 1,000 hours. So for a bit of context, think about lights, let's say in your lounge or kitchen maybe. Those would probably be the two areas where you're likely to use your lights the most. In the winter, you might turn those on at, let's say, 6 p.m. and then depending on what time you go to bed and switch everything off, you're probably running those lamps maybe till 10 and perhaps 12 o'clock. If it's my house, you switch them on at 10, you switch them off at 7:30 when I go to bed. But maybe you guys stay up a bit later, I don't know. So we're probably using, and then certainly in the summer, that equation changes. We're not going to be switching on our lights until maybe 8 o'clock at night, and then you might only run them for a couple of hours. So if you average it out over the year, you're probably looking at between 2 and 4 hours per day for the most used lamps in your house. Given that there's 365 days in a year, so 2 hours a day would equal about 700, but over 700 hours. 4 hours a day would be about 1,500 hours. So for the lights that we have in the most used areas in our house, we're looking at somewhere around 700 to 1,500. Probably somewhere in the middle would be about the average usage of those bulbs. So 1,000-hour incandescent is probably going to last us around about a year. If you look at the least trafficked areas in your house, bathrooms, maybe hallways, bedrooms as well. You think bedrooms, you use the lights quite a bit, but really, they're only going to be when you're in there. So given that most of us go to our bedrooms to sleep, 1 to 2 hours a day would probably be, even 1 to 2 hours a day is probably more than most of us would use the lights in our bedroom. So then we might be talking about a couple of years. So that tells us then that the average lifespan of an incandescent lamp, depending on where it's installed in our house, should be something like 1 to 2 years, which sounds about right. It seems like quite a long time, but if you think about it, particularly in a modern house, I think we did a little experiment the other day where I asked you to try and count up in your head how many lights you had in your house. Some people have said maybe there's about 10 to 15. More modern houses, you're looking, big, a decent sized modern 4-bedroom house with downlights, you might be talking about something like 30 to 40. So you've got 30 to 40 lamps in your house and your average lifespan of a lamp is 1 to 2 years, then we're looking at changing anything from maybe 15 right up to 40 lamps per year. So even at the low end there, you're talking about replacing a lamp every month, at least one lamp every month. And if you had 40 lamps in your house and you're getting 1,000 hours out of each of them, then you might need to replace all 40 in a year, which means you might have three or four lamps per month. The reason I point this out is because it's a question that you'll get asked a lot. I think this is actually the most common question I get asked as an electrician. by people that I know, which seems ridiculous, but here it is. Why do the lights always blow in my house? Everybody seems to have this weird idea that their lights blow more than everybody else's, and that somehow they've got some weird power thing going on. My opinion on this is that you don't have a weird power thing going on. Wire is wire, voltage is voltage. You're getting voltage to your house. If you had some sort of weird power thing going on, you'd notice it. You'd notice it on sensitive appliances like electronics and stuff way before you'd notice it in lights. Lights don't really care. It's just a filament burning. So you could put an ordinary 230-volt lamp onto 100 volts probably, and you wouldn't get the light output, but it will sit there and burn quite happily, right? There's nothing voltage sensitive about that. Frequency is not going to do anything. Maybe if you got weird voltage surges, you might pulse that lamp and burn it out, but it's really unlikely. What's actually happening is people are underestimating the number of lights they've got, and they're overestimating the lifespan. So the reason I point out that a modern house might have up to 40 lamps, which are on average going to last 1 to 2 years. Like I say, that might mean you have a lamp burning out 3 or 4 lamps a month. 4 lamps a month would be 1 a week. So if you've got enough lights in your house and you're using incandescents, it would not be uncommon to have a lamp going out every week. There's nothing to do with your house. That's just a function of the number of lights. Well, it's nothing to do with the power coming to your house. It's just a function of the number of lights that you actually have and the lifespan of them. I have never, ever in my life found a house that has something wrong with it that causes the lights to blow. But as I say, that is by miles the most common question I get asked from people who go, "Oh, you're an electrician. Why do the lights always blow in my house?" Yeah, so I guess maybe I'm a bit sensitive to that. But it's a good little mathematical thing to understand, because you guys are going to get asked that question too. And it wouldn't actually surprise me if at least one of you haven't already had that question by somebody. "Oh, you do an electrical course. Why do all the lights blow in my house?" Yeah, if you get asked by anybody, let me know, because it'll validate my position. So there you go, and I guess it also illustrates how unreliable that technology is. How piss poor it actually is, that you would just be continuously blowing light bulbs all the time, just because they don't actually last that long. So the lifespan can then be affected by the mounting position of the lamp, heavy vibration, ventilation, and variation in the supply voltage. So mounting position of the lamp might mean, would there be the ability of that lamp to dissipate heat. We know that the lamp is going to produce heat, and we know that heat will degrade the lifespan of the light bulb. So the way it's mounted in terms of the ability for it to dissipate heat is going to affect the lifespan of the bulb. Heavy vibration, yeah, that filament is very small, and any movements in there can cause it to break. Ventilation is to do with the heat dissipation as well, and variation of supply voltage. Although I've just poo-pooed the idea that you blow all your lamps because there's something wrong with the power to your house, it is possible. You may get fluctuations in supply voltage randomly from time to time. Again, I would heavily contest that means that any given house over any other house is more prone to it, but supply voltage or variations in the supply voltage may exist from time to time randomly, that coming from that generation facility. This table here shows common lamp caps, so that's the type of connector, and lamp holders used in New Zealand, and the maximum voltage and wattage of lamps for which they are designed. So we had a look at this last week, right? The different sizes of connector. The ones that we decided, or that I told you, were the common ones, so the E27, which is the second one on the table here, and B22. So those are standard sizes. For the Edison screw, the standard size is E27. For the bayonet is the push and twist one, is a B22. So as you can see, that the maximum lamp wattages different depending on the size of the connector and so forth. You can get issues from time to time. I think I've once in one house that I lived in, it was like quite a big kitchen with just one single bulb, and I think I put a 150-watt bulb in there. I think I tracked one down, and that did eventually melt the fitting, and I had to replace it. So it is something to be aware of, that you can't just throw any any wattage of lamp into any fitting. If you got those table lamps with the fabric shade on them, you want to use lower wattage lamps in those. I don't think anyone is sticking 100-watt bulbs in those, because that'd be crazy. You just have this massive bright light sitting next to your bed. But be aware that the heat dissipation out of those is obviously reduced, having that shade all around the bulb, and those shades don't tend to be particularly flame retardant. They're just usually made out of fabric. So don't stick a 150-watt bulb into those, please. And here are the drawings of those various types of bulbs, including the measurements. Again, this one here is our E27. That's the common size there, and there over on the right-hand bottom corner is the B22, which is our standard size bayonet fitting. So a note on the safety of Edison screws. We've talked about this. The Edison screw lamp holder must be connected to the supply in such a way that the phase conductor is connected to the center terminal and the neutral is connected to the outer threaded section. Again, if we don't remember that, that's because if I stick my hand inside the fitting to unscrew the bulb, the outer thread here, this part that we can see here, is one of our terminals. So if that's the phase terminal, then I could potentially stick my hand in there and touch that thread while it's still connected to the supply. So we're always going to make sure that outer thread is the neutral, and then the inner there, you can't really see it on this picture, but it's the end cap there, that will be the phase. The phase is always connected to the center. So when you're looking at your Edison screw fitting, you should see that one of those terminals in there is connected to the center pin, and one of them is connected to the thread on the outside. Always make sure the center is phase and the outside is neutral. So here's a little picture. These are great little pictures here. We've got one of these for every single type of lighting, which I think is fantastic. If you look on the right-hand side here, you'll see this is the spectrum of light or spectrum of radiation, I guess, that exists in the universe. So right down here we have the very long waves, which we use for radar, TV, and radio, thermal radiation, ultraviolet, X-rays, gamma rays, which have very high frequency. So we're talking about the wavelength, or frequency is another way to put it. Right here in the middle, this tiny little section here is that is the spectrum of radiation that is visible to our eyes. And then we'll be familiar with this color pattern here: red, orange, yellow, green, blue, indigo, violet, and up to white. So those are the colors of a rainbow, right? So different colors represent different wavelengths of light. The longer the wavelength of light, it shifts more towards white, and at the short end is red. That doesn't mean anything in any objective context. It just means that that's how our eyes and our brains perceive the different wavelengths. So color really, if you think about it, is something that just exists in our heads. So then the picture on the left here gives us the spectral curve of a typical incandescent lamp. So this is how much the graph represents here, how much light we are getting from each of the colors on the spectrum. So you can see here that the incandescent has a lot more light output in the red-orange end of the spectrum, and relatively low output at the purple and white end. Which means that, if you haven't figured it out already, when I look at an incandescent lamp, it's got that characteristic orange tinge to it, right? It looks orange to us because we're getting a lot of light at the end, at this end of the spectrum, not so much at this end. And you'll see when we go into the gas discharge, in particular, that we can get some really weird looking graphs here, like some of that low pressure sodium that I talked about that has that really yellow light with the poor color rendering. You're basically getting nothing across most of the spectrum, and this big spike in the yellow, because and that's all you get. So even though the total output of this is all mixed together, right? So we're not seeing it as being red, because we've got these higher frequency lights coming through as well, which soften or whiten the color. So we get that orange-ish, but it's not completely orange. And because we've got every color in the spectrum here is represented, at least in some degree, then we're going to get pretty good color rendering, because we're able to the color rendering is a function of the light in any given spectrum. So we're at least getting some light at every part of the spectrum, which means that the incandescent, although it looks a bit orange, is still going to give us pretty good color rendering. Efficacy of tungsten filament lamps. Efficacy, remember, efficacy means our light output per watt. Efficacy of a tungsten filament lamp is very poor, as these lamps give off a tremendous amount of heat. I mean, not a tremendous amount. You're not going to turn on a light bulb and it's going to, heat your whole house. But in comparison to the amount of heat we want out of a light bulb compared to light, these are pretty poor. And when I say the amount of heat we want compared to light, we want zero heat and only light. So the reason that a standard incandescent is pretty inefficient is because it's producing so much heat. So a lot of the power that we're burning is being used to produce heat rather than light, which we don't want. So it becomes an inefficient form of lighting. Gas-filled filament lamps or halogen lamps. In a gas-filled incandescent lamp, the bulb is filled with an inert gas, usually argon or nitrogen. The molecules of the filament collide with the molecules of the gas, and the gas conducts heat more readily from the filament to the glass bulb, and this action will cause light. Adding a halogen vapor to the inert gas that fills the filament lamp and using a higher operating temperature produces a chemical reaction cycle in the bulb called the regenerative halogen cycle. Halogens are a group of elements consisting of iodine, bromine, chlorine, and fluorine, where iodine is the most widely used. Longer life, lack of deterioration in lumen output throughout the life of the lamp, and improved luminous efficacy are major features of the tungsten halogen lamp. So halogen lamps are the little spotlight type ones, right? Or you get the outdoor longer ones, 4 or 6 inches long. So they have a gas inside them that, as it says in there, is used to improve the light output and the life of the filament itself. They tend to, as it says there, they tend to run hotter. These are the ones that I said last week. You don't want to touch the glass because the oil on your fingers will cause it to overheat. Then here is a typical. This is the outdoor type ones that I mentioned. So that's your long bulb. We've got the same tungsten filament in there. And that is filled with that inert gas, that argon or nitrogen, mixed with some sort of halogen gas. So here's the light spectrum output of our halogen lamps, which if you look at that very closely, you'll notice that that is essentially identical to the incandescent one, because it's still a type of incandescent light. And although it's a poor quality picture, this is the type of outdoor fitting. I think I mentioned this last week and most of you gave me a blank look. This is the type of outdoor fitting which has that long halogen tube. It's still an incandescent. It looks like a tube, but it's the same concept. It's got the filament inside there. It's just that the bulb is a different shape. So as I said last week, you tend to see these outdoors. You can see that this one is in fact a motion activated lamp, or motion activated fitting, so it's some sort of security light. They're handy outdoors because they punch out a lot of light, right? These things, as opposed to a standard incandescent in your house, which would be somewhere between 60 and 100 watts. These tend to be anything from 150 up to perhaps 400 watts. So they're pushing out a lot of light, which is handy outside, right? These are various other types of halogen lamps. So there's at the bottom there, there's the same ones we just looked at. That's the longer one. The one in the center there is our typical domestic spotlight, typically used in kitchens and that sort of thing. This is a similar sort of thing, but obviously it's just the tiny little bulb rather than the whole casing as well. And this is, I guess, a type of halogen downlight. So the handling, we've talked about this before. You must not touch the glass of these lamps with your bare hands. The oil on your skin stain and degrade the quartz of the glass. With the high operating temperature of the lamp, the contaminated quartz glass develops fine cracks, leading to early failure of the glass and the lamp. When installing lamps, handle them by their ceramic ends. So that's those long ones that we just looked at. They've got little ceramic bits on the end which you can hold. Or use the dry wrapper paper material. So, and I think I mentioned this last week as well, they usually come with a piece of paper inside. Maybe the lamp will even be wrapped in a piece of paper which you leave on while you install it and then pull it off. If you do accidentally touch the glass, give it a clean with a solvent such as industrial spirit. So you could use meths or white spirits or something like that. Just give it a wipe to just remove those oils off it. If we're talking from a cynical point of view, I mean, if you're installing halogen lamps for someone other than yourself, then it doesn't really matter that much, because whilst you might degrade the life span of that light a little bit, what are they going to do? They're going to ring you up in 6 months and go, oh, the lamp you put in blew earlier than I expected. You have to replace it for free. And then I would turn around and go, and there's so many variables going on here. There's no way that you can prove that I did anything. I'm not replacing shit. But maybe I'm just a douchebag. Halogen lamps are somewhat more efficient than incandescent lamps, but operate at an even higher lamp temperature. So you get some efficiency gains from the halogen gas in there, but obviously you'll lose some as well because of the heat, because they're even hotter. And this is a point to note, that on a normal incandescent bulb, if you touch that when it's running, it'll burn you. If you turn it off, you leave it for a few minutes and it'll cool down pretty quick. With a halogen lamp, they operate at a lot higher temperature, and they will hold on to their heat for a lot longer. So just be aware of that, right? You don't turn a lamp off and then try and replace it straight away. Give it time to cool down before you touch it. Low voltage lamps. So low voltage lamps typically operate at 230 volts as standard voltage, connecting them directly to the supply voltage coming in. So this is a GU10 base, which has a twist and lock mechanism. It can also come as a tube, making them ideal for floodlights. So I've talked about this before. This is our GU10 base here. So we've got the two weird little pins or stubs sticking out the bottom there. You push it in, twist it like a bayonet cap fitting. Push and twist. There's a 230 volt fitting. There's a GU10 base. We also have extra low voltage ones. So they typically operate at 12 or 24 volts. Transformer is required to step the voltage down. So when you buy a extra low voltage halogen lamp fitting, it will come with a little transformer like this. It'll drop that voltage down to 12 volts. It does introduce another point of failure into the lamp itself. Sometimes the transformer blows, not the lamp, so you have to replace the transformer, although typically the transformers will last a lot longer than the lamps themselves. Adequate ventilation is required for the transformer. So the transformer is going to sit inside the roof space. You'll typically only have a short length of wire between the transformer and the lamp. So 230 volt TPS comes into the transformer, and then you have and the transformer changes the voltage down to usually 12 volts. And then you have a short lead coming out of the transformer to go to the light bulb itself. It's got to be aware of where you position that transformer. It's going to create a little bit of heat itself. So we don't want to bury those under the thermal insulation in the ceiling. Is probably the key point here. You sit them on top of the insulation, not underneath. Otherwise, you're going to reduce the lifespan of that transformer because it'll overheat, and then there's also a fire hazard.
Hey Dan, just quick.
Other type of pin arrangements are available for other applications such as automotive lamps. However, the standard is this one here. So you'll notice that if you look back at this one, that lamp there and this one here are more or less identical, and that is the case in real life, that those two different types of spotlight will be virtually identical. The difference is the connection. So this is how you know. If it's not written on there or it's been rubbed off, you can see this one's got writing on it, which will tell us what the voltage is. I can almost read that. It looks like 12 volts to me. But if you've got an old lamp, you might find that that writing has rubbed off or worn off. I can tell, well, there's two ways I can tell, right? One is if it's connected to a transformer, then it's going to be a lower voltage. But even if you're just pulling the bulb out and you're not looking in the roof, you can see this one here has the 2 pins, so it just pushes in. And this one here has the push and twist. So that's an industry standard. There's nothing about those two different connections that make one 12 volts and one 230. It's just an industry standard. This one here, the GU10, is 230 volts. This one here, MR16, is the 12 volt. It might seem a little bit obscure now, but I promise you this information will come in handy one day, even if just showing off. Because your mum might ask you, oh, I've blown this light bulb, what type do I need? You say, oh, that's a 12 volt MR16, mum. And you write it down, 12 volt MR16, take that to Bunnings. They'll help you out. There you go. Good stuff to know. Okay, a question here from Jade. Can a faulty transformer cause your lights to flicker? Yes, a faulty transformer can cause your lights to flicker. Particularly if you're using LEDs. So again, although we're talking about incandescents here, and this transformer is specifically designed to operate a incandescent lamp, you can buy LED bulbs like this MR16. So an LED bulb that looks exactly like that. That is a straight one-for-one replacement with a standard incandescent. LEDs are a lot more sensitive to voltage fluctuations or voltage changes than an incandescent. As I said earlier, an incandescent is just a burning filament. So you turn the voltage down, you won't get the light output, but the lamp will still work. Nothing happens because it's just burning voltage, whereas an LED is an electronic component, so it's much more sensitive to voltage. It needs certain voltage to operate correctly. So if you've got an LED bulb in a standard MR16 fitting with a standard MR16 or a standard 12 volt transformer, then as the transformer starts to crap out, then your LED is going to flicker, and it'll be quite weird, like it'll flash on and off like quite a steady rhythm, or can do. If the transformer output is starting to fade, then we can get fluctuations of output from the transformer, and that can cause even a normal incandescent to start to come on and off. But if we're talking about flicker as in the light specifically turning on and off, that's probably that's quite a rare occurrence with an incandescent, because as I say, the incandescent it just burns a filament, so it's a lot more resilient to changing voltages. If we think about the fact that our voltage, AC voltage in New Zealand, is coming on and off basically, or positive and negative every 50 times a second, one of the advantages of an incandescent is that it will take a little bit of time. I mean, 100 milliseconds or something for it to come to full brightness, and then also for it to fade to zero brightness after the power is removed, right? So that flicker of 50 times per second is much faster than the actual element, or the filaments in the incandescent bulb can flicker on and off, because it's going to, at a very, not perceivable to our eyes, but if you were to slow it down, you'd see that bulb take a little bit of time to get the full brightness and a little bit of time to go down. So even a voltage fluctuation to an incandescent bulb is not going to necessarily cause a flicker that we would perceive with our eyes. It would have to be quite a long fluctuation to cause that. We might get slight changes in brightness, but probably not an on and off flicker. So whilst, yes, Jade, the answer to your question in simple terms is yes, in real terms, it's going to be quite a strange circumstance that would cause that. And I strongly suspect that if you're getting flickering, like genuine turning on and off, flashing, if you like, it's probably an LED bulb, or and in that case, it's more likely to be the bulb than the transformer. But it might be the transformer. Yeah, maybe your house is haunted. Yeah, if they're randomly turning on and off, that is probably not a transformer. That sounds more like a either an LED that's on its way out, or if it is an incandescent, then it sounds like it's more like a poor connection, like something is not touching where it should. Now that could be anywhere. That could be in the light fitting itself. It could be where the wires are connected to the transformer, both the incoming and outgoing wires from the transformer. Or it could be something faulty. It's possible that it's something faulty in the transformer itself, but as I say, it's more likely to be a connection. Now, if you have multiple lights doing it, it could be in the switch. So if the wire inside the switch is bouncing around inside the terminal, because we haven't screwed it up tight enough, or it's come loose over time, then that could cause the lights to come on and off. But then you'd see, obviously, all of the lights do it at once. Is it all of the lights do it together, or do they randomly do it at different times? If it's random, then it's probably more to do with the bulbs, I would suggest. I wonder whether they're LEDs. Check whether they're LEDs or incandescents, and let me know. We can fault find this. Yeah. So I can't tell you the specific answer for your house, but as I've just said, there's various reasons why that might happen. But if you're interested in figuring it out, I'm interested in figuring it out too. So start with checking what type of bulbs are in there. Even take a photo maybe, and let me know, and we'll see if we can figure it out. Are you happy with that answer? Should we carry on? Oh, I didn't necessarily mean right now, but okay. Did you just literally take that photo right now? Nice. Okay. Okay. So this is a MR16 fitting. If everybody's watching, so you can see there that this does not have the push and twist. This is if I go back a slide. If you're wondering what I'm talking about, you can't see it. This is Jade has just posted a picture in our chat. So I can see there that this is the push pin type fitting. It's on a slideshow now. So that just pushes into the little ceramic fitting at the top. I can also tell that this is, well, I know that it's a 12-volt fitting because it's a MR16 bulb, but also because you see the two white leads coming off the top there. That tells me that they're going up to a transformer. That's not normal. That's not normal 230-volt wiring, right? If it was 230 volts, we would see the black and the red TPS coming in. So that looks like a standard MR16 halogen. And in that case, it would be unlikely that they would randomly turn on and off due to a fault in the bulb. I suspect then that you're probably right. It is more likely to be the transformer. Unless they're all coming on and off together, in which case there'd be something wrong with the switch. If you want to try replacing a transformer, I could supply you with some transformers to take home and test out. Let me know. Next time we're back in class, let me know if you want to grab a transformer, and I'll find some for you. Cool. All right, let's carry on. Okay, summary. Incandescent lamp. The filaments of a modern incandescent lamp are made from tungsten because it has a very high melting point, so it's resilient to heat. In a gas-filled incandescent lamp, it's a halogen. The bulb is filled with an inert gas, usually argon. The gas greatly reduces the evaporation of the filament. To reduce the cooling effect of the gas, the filament in a gas-filled lamp is wound in the form of a coiled coil. An incandescent lamp is said to emit a continuous spectrum, so it gives that lighting across the spectrum, gives us good color rendering. The average lifespan of an incandescent lamp is 1,000 hours, depending on the mounting position, vibration, ventilation, and variation in supply voltages. A tungsten halogen lamp operates at higher temperatures than an incandescent lamp. The process, called the regenerative halogen cycle, maintains a constant level of lumen output throughout the life of the lamp. Where a center contact bayonet or Edison screw lamp holder is used, the outer or screwed contact must be connected to the neutral or earth conductor. So we're always putting the center terminal as the face. So that is that slideshow is over. Pretty quick one. Okay, so I'm happy for us to end that one here. Do we have any questions? Any other questions? I appreciate the questions we've had so far. That's good. Always good to have questions. I think it makes it much more interesting. Otherwise, I just have to talk to myself. It is quite a strange experience. I might have said this before, but it's quite a strange experience. Although I know that you guys are there listening, I can't see anybody, so I'm essentially just talking to the wall. And I try my best to make it, sound interesting and construct a little narrative around it. But without even just the feedback I get from looking at people's faces in a classroom, it's a very different experience to deliver a lesson to a computer. So whenever I get questions from you guys, it does honestly, genuinely makes it easier for me. And I'm certain that makes it more interesting for you guys as well. So do we have any questions for anyone on this? No, everyone's happy. Okay, what we'll do then is we'll break for lunch. As I said, we will carry on this afternoon and start on the next topic, which is gas discharge lighting. Let me just grab that slideshow while we're still sitting here. Okay, so the next slide shows about 50 slides. It's about 3 times longer than the one we just did, which we got through in about an hour. So I reckon it's about a 3-hour lesson, this one, the next one. So we'll do an hour to an hour and a half after lunch. That should get us about halfway through. And then we'll stop for the day. We'll finish gas discharge tomorrow. I'm going to make the call now that we won't be in class tomorrow either. I think I'll go and get a COVID test this afternoon once we're finished. I don't think I've got COVID, but just to make sure, I'll go and do that this afternoon, which will mean I don't think it'll be a good idea to go to class tomorrow. So as long as everybody's happy, we will continue online tomorrow as well. And then hopefully Wednesday, I can get my shit together and come back to work so that we can carry on with our practicals on Wednesday. So I'm going to say, let's take a little bit longer for lunch. Let's come back at 1 o'clock. And with that little extra 15 minutes or whatever, however long it takes you to have a feed and come back, I want you to watch some of the videos on the gas discharge page in Canvas. As I said earlier, those are really good videos. And I think it's really important that we check those ones out. The gas discharge stuff is quite technical, and I'll be honest that some of the technicalities of how gas discharge lamps work are beyond me. So you're going to get a lot better information out of those videos than you will directly from my mouth. So just having a quick look there, it looks like we've got about 30 to 40 minutes, maybe about 40 minutes worth of videos on there. There's 1, 2, 3, 4, 5, 6 of them. So please take the opportunity while we're at lunch to at least watch a couple. yeah, so if you click on discharge lighting, you'll see that it's got the PowerPoint, the read me button, and then you've got the watch me buttons there. Yeah, so go through those. I don't expect you to watch all of them, but please at least watch a couple. And you know, if you can bring some questions back from those videos too, that would be good. All right, that's enough out of me. Once again, I'll leave this. I'll leave the video or the meeting open. I'll just turn off my microphone and video. So we'll come back at 1 o'clock. So go and have lunch, watch a couple of videos. See you back at 1.